All right. Okay. Last Tuesday, we end on this question here. For number 1, define tangent at point. I think it can be done easily. You just find the dy over dx, okay, using the chain rule, and you are using the theta as the parameter, not t. Okay, you can use theta, and use theta equal pi over 3 for evaluation. Okay, and then you get the value. Okay, and eventually, after you get the gradient, you get the tangent, and you can put into the slope. Okay, you can put into the slope. Okay. The position of x and y, you can also input the theta into the parametric equations, and so you get the positions. So you get the final equations for the tangent line, right? Okay. Number 2, at what points is the tangent horizontal or vertical? This is similar to the previous question. So we are going to have, I can write over here. Make it bigger. So horizontal tangent is when the slope is 0, right? The slope is 0. But in our case, if we look at the parametric, then we will have 2 components, right? We will have 2 components. Okay. To make this component 0, okay, to be true, then this top equation here should be 0, right? And this one not 0. Okay. So that's the horizontal tangent. And we will finally get the theta after we evaluating this, okay, from the dy over dt equals 0. And you will get the point on the cycloid. Okay, the point on the cycloid. Okay. Let me write the results for dy over dx. From our calculations, we get this is sine theta over 1 minus cos theta. So theta can be 2 pi n, right? If you look at the cycloid, if you remember, this is our graph, right? At least roughly sketched, that's our cycloid. And if you look here, if we zoom into our cycloid here, of course we see clearly that is horizontal tangent, right? Horizontal tangent here, here, and here. And how about the vertical tangent, maybe here? It seems that there is a vertical tangent. So, what can we do? We then verify if this is 0, when the cycloid is 0, it should be having a theta around here, right? 2 pi n. So it should be around 2 pi r, 4 pi r, and you can multiply when the position is at 0. Okay. And the first question is maybe around here, that is the theta is pi over 3, which is we have the tangent line here. The last Tuesday line, right? Probably around that point. Okay. Now, if we observe the line around here, okay, or maybe here, the vertical one, okay, we can actually approach those vertical line through or using limit. Okay, we can approach that using limit. Okay? So we can have a limit as theta going to have 2 pi, we can have more, let me check, 2 pi n from the, maybe from the right side, okay? And you can confirm this also from the left side if you would like to. Okay. Now, of course, what we are doing here, if we remember the last semester, the calculus 1, if we check, this will be a 0 over 0 situation, right? What we can do is, this is our indeterminate forms. That's why we can do the Logitech rule. Then we can derive each of the sine and 1 minus cosine. So we can have this will be cosine, and minus cosine becomes sine, right? Okay. Now when we are doing what we are doing here, the cosine becomes 1 and the bottom one becomes 0, in which this will be the undefined situation. This will be an infinite, or we are going to have an infinite value here, which means that the vertical is true. The vertical tangent is true. That when we are approaching the certain point, we have infinite value. So that means that it seems that the vertical tangent is true at limit as theta approaching the 2 pi n. Okay. This n is can be any multiplication of the cycle length. So it seems that it's true that it has the vertical tangents. It's true. It's true that it is having a vertical tangent. Okay, so horizontal tangent when slope is 0, and vertical tangent when slope is actually having similar to like an asymptote. So it has an infinite point. Okay. Now, before we move to the next one, which we are going to learn about the area or integrations in parametric, let me just review a little bit from last Tuesday, just a little bit, what we have done last Tuesday. Okay. For example, okay, we know that we have a parametric equation, and let's say we have, for example, okay, this is the last Tuesday example, I think. Just to recap what we have done so far. Okay. There are several ways to see what this is. Okay. Remember that t, it can be any variables. We call the t is a parameter. T is a parameter, right? T is parameter. sometimes to make it simple, you can say t is like time and x, y is a position. Okay? So you change t, you can change also positions, like in physics, if you remember physics. Okay, so to solve this, if you want to check or you want to find the slope, okay, so suppose that x and y is a functions of t, and y is also a function of x. Okay, so x, let's say this is t, and y is also a function of t. Then we know that we can directly get these forms, right? Okay, we learned that last season. But before doing this, we can also eliminate the parameter. Okay, we can also eliminate the parameter. For example, t is y minus 1, right? And then we can input this. Right? And then we can get that this is okay. And of course you can do your implicit differentiations, and still you can get dy over dx, right? Second way to see. Another way, this is quite tricky, and maybe it will be helpful for some cases. Okay? Maybe it will be helpful. See this. Okay? See this. Please observe this. It's a technique usually called the complete standard form. Okay, let me use this. So, looking at the y squared minus 4y plus 3, okay, I want to make this, the whole thing for y, the quadratic equations here, I want to make it a complete square, which means I want to have this in terms of something squared and it's become this. Okay. So, see here it's negative 4, it's 4, we divide by 2, we squared, so it should be 4. So it should be 4 around at this one, so I need to plus 1, right? And I need to plus 1 here, okay? So this becomes 4, okay? Wait, this is confusing, this is 4, okay? So this will be, okay? If we take square root both sides, we can also write, let me just write x, the square root x plus 1. This will be y minus 2, and we can write this in terms of 2 plus square root of x plus 1. Sometimes this also can help if you want to eliminate, okay, okay? And you will get directly the expressions in terms of y and function of x. And of course, if you would like to check the tangent, you can apply just normal derivatives, and it will be okay. So it's also true. So actually, there are several ways you can look on, and you can try. Okay, you can directly using the chain rule to have the parametric calculate with calculus, or you can eliminate the parameter, and you can have at least several ways to eliminate the parameter. for derivative, I think there will be not really much problem to derive. Okay? But if we want to integrate, I think that would be difficult. That would be difficult. Okay, so this is just a recap of what we are doing. And remember that if you want to have the second derivative, we start from this. Okay? Now I can think we can move to the next sections. And be careful on the second derivative or the next derivative after that. Okay, can move to the areas. Let's say we have a curve, okay, and let's say area under the curve from A to B. Let's say we have a definitions from the calculus one, that is right, okay, where the function itself is a positive. Okay. Now suppose from this, suppose we can also trace the curve with parametric, with some parameter, with t, okay, as a third variable. So suppose we can have the parametric and we can have the t varies from alpha to beta, okay. Then from this area, or let me write just y, okay, y is function of x. We can exchange y with function g. Okay, we can change that. And dx, we can change with the dx from here. We use the chain rule. We derive the x, and we get this is. Let me just write f prime t, which means the derivative of the function f, okay, and dt, okay? And we can exchange this into our t. Okay. Basically, you can think the dx as your chain rule from this function, from the supposed function of the parametric. Okay? So you can exchange dx this is actually the f from here. Okay. Well, this alpha and beta can be like this, or it can be beta alpha. It depends on the situation. But generally, we can write like this one. Okay. Okay. I just try to have the from the cycloid we have done. Let's say we want to check this area here. Cycloid is x, r. So if you write roughly the integral, the area will be from 0 to 2 pi r of y dx. And now we need to exchange y in terms of new variable, which is theta, okay, from the parametric equations. And we also exchange the x from the derivative of the parametric x, the equation of x. So with substitutions, that is y is r1 minus cos theta and dx is become r1 minus cos, right? So it's become r. And now the endpoint also changing, because we only look at the now only theta, then we can have the theta from 0 to 2 pi. Okay? 0 to 2 pi. think we can solve a little bit algebra. Okay, I hope still remember how to integrate. If you look this quadratic here, we need to use double angle formula. Okay. Need to use double angle formula. Let me remind you the double angle. So we can exchange this cos squared with cos 2 theta. Okay. So we will have one minus 2 cosine theta plus half 1 plus cos theta and d theta. Let me check this with d theta, 2 sine theta. This is half. This is sine 2 theta divided by 2 and 4, right? So this will be 1 plus half 3 over 2, I get correct? From 0 to 2 pi. Still we have r squared and we can input 3 over 2 pi, and then the other one still 0, right? Because it's sine, so 2 pi 0, 0 also becomes 0, so this is the only numbers that we can count. Okay, if you look closely from here, let me just write here. Okay, what we are doing here, we are just manipulating the chain rule. Okay, if you agree with me, we are manipulating the chain rule within the parametric curves. Okay, so we want to have the integration with dt, right? We want to have integration with dt, right? And still, if this is y, and we want to change from y function of x into function of the parametric, because that's basically the same curves, we can write this. And to make it sensible in terms of the writing, then we can make this into dx over dt, okay? Right? Okay? We can also look on to that perspective. So it's just a manipulation of the chain rule that we already learned, okay? So that's why the formula becomes like this. Okay? This is actually the same thing here, okay? I think this is easier to comprehend, because this is actually, we have done the chain rule, and this is just basically manipulating so that this terms is equal with this. But of course, this is changing into another variable of t that we want to evaluate. Okay, I think we can go to the next one. Okay. So basically, I will have a little bit review for sum of calculus 1. Okay. Next one is the arc length. Let me just go drawing the random curves. Okay. And let's say we are pointing out the tangent here. Okay, yes, our tangent line. And if we imagine this line to be really small, okay, and we mention this as a dl, we have two components from this dl, that is the dx and dy, right? Okay. Now, if you remember that to make this arc length formula, we can start with this triangle. And then we can set to measure dl, square root of this, right? And let's say we divide all by the dx squared. Okay. And I'll factorize the dx outside. So we'll have 1 plus dy over dx, this is squared, and then dx at the end. Okay. This is intuitive definitions of the arc length, and I think it will be much more easier rather than look on the with the graph or the official definitions as in your textbook. Okay. Now we integrate the dl so that we are evaluating all the length measured. Let's say we are evaluating from A to B, or from x1 to x2, and that's also fine. So we get right A, B. Okay, that's the original arc length. Okay, the original arc length. Just I refilled a bit. Now, how about the arc length in parametric? Okay. So arc length in parametric. Let's say we start from dl, and we also start from the same thing as in the original arc length. This is start from, let's say, dy squared plus dx squared. Let's start from here. because y and x is also functions of t, right? Again, in the parametric, we can also manipulate all those terms with the chain rule. So we can have something like that, and dx over dt multiplied with dt. Okay. So basically, these two arc lengths basically the same. But the difference is because we can trace the curves and make it into a parametric curves, we can also make it into the derivative and integral equations. So we can make out the parametric equations from the derivative and integral. Okay? So we can exchange, and we can further we can factorize the dt. Or maybe the dt should be at the behind, so that the integral seems true. Okay. Or we can simply write, maybe this is t1, t2. You can simply write the y prime t squared plus x prime t squared. Okay. So whenever you find any equations, and maybe they are already defined as a parametric equations, definitely you can go for another way, this way. Okay. If suppose that the equation is true, that it's parametric equations. Okay. Well, in your textbook, you are using the alpha and beta. We can also write the same. We can write also with alpha and beta. And there are several definitions with limit, but I think we already done the definitions in calculus 1, so I don't need to write. Okay, I think I don't need to write all the complete theorem. Okay, this is supposed to be y is function of t, x is also function of t, and they traverse with certain variable or parametric, or so some parameter t. Okay, let's say it's alpha and beta, and we can write the arc length as simple as that. Okay, to check on how we are understand how to use the arc length, we can try to look on the example. Okay. Of course, we already see the curves that is being a circle, right? That is a circle. But let's say we are going to have our calculations on the arc length. So our arc length this is sine squared t plus cos squared t and then dt. And it turns out that this is giving you the 2 pi, which is the circle, right? The length of the circle, right? The arc length of the whole circle is 2 pi, right? And there are several, not several, maybe just one notes, okay? One notes regarding the arc length. Length, not length. Make sure that the curve is traversed only once as t increases from, let's say, alpha to beta. Okay, what does it mean? It means that in some certain conditions, case, something like this circle, we can have like several rotations, right? So we need to make sure that it's only one, so that we can have that. Of course, we say that this is 2 pi. That's the maximum that the circle can have, right? But in some cases, if we calculate and our calculation seems like maybe 8 pi, we are four times circling around, which means it doesn't make sense, right? So we need to make sure that it's traversed only once. Okay, aside from the just regular arc length, on the calculus 1 we also learned about the arc length function. Okay. Okay. Let me write some notes here. Arc length functions gives length of the curve from initial point to any other point on the curve, which usually in calculus when we symbolize or we make it into some x. Okay. So it doesn't need to be the exact length, but it can be any terminal point, any end point. Okay. let's say, suppose the x is function of t, y is also function of t with g, let's say function g, and we set the first derivative to be continuous, and we let the st is arc length along the curve. Let's say from initial point, maybe t equal alpha, or xy is f alpha g alpha. To point ft g of t. And we can write st as alpha to t. So just exchange the endpoint. Okay? And because we already used t in our parametric, we use another variable, let's say du, okay, to set the equations. Because if we set with another t, we will have some confusions, right? All right. Now, just some notes here. That if we are going to think the s as a distance in the physics, we can get the velocity as in the s prime, and we can get the directly these terms. Okay. I hope you still remember why this du becomes t because of the fundamental theorem of calculus. Okay. Okay, that's the arc length functions. Okay. Now the other one is called the surface area. Let me just write. This is actually the same thing. Suppose this is the function of t. And f prime and g prime are continuous, and gt is a positive. And curve C traverse exactly once. As t increases from alpha to beta. Okay, let me just draw some simple curve to illustrate. This is from calculus 1. Let's say we are going to rotate here about the x-axis. So rotate here, then the surface will be 2 pi 1. And then let me just write directly using the alpha beta for the t. So basically the same, but we just change the arc length. Change the arc length. We change according to the parametric one. Okay. This is rotated about x-axis. If rotated about y, then we can have this becomes 2 pi x and then ds. And the certain parametric, it depends on how the functions will be, how the functions in cases. Okay. But basically, all the calculus 1 formula, it's still we are going to use them, but we are changing some parts into a parametric. Okay, to the parametric. Yeah, sometimes write ds or el, but of course this part here is the arc length. This is rotated about y-axis. And the nodes also the same as the arc length, so that the curve should move or traverse exactly once. So whenever you find maybe some questions, they are asking the surface area or asking the arc length, but you cannot find like maybe from where to where, and you need to guess or you need to try to find the end point. You need to be careful so that the curve should exactly just one time. If you take the t, maybe more than, it can make the curves or it can make the movement is maybe they will have repetitions, and that makes the calculations wrong. Like this a circle, that's just 2 pi maximum. But when you maybe using different t, you can have like 4 pi or 8 pi and make the calculations seems wrong because the circle has that too long. Especially if you have some curve that has some lot of curves, you need to be careful on. Okay. Okay, I think we can move to the polar. And later, maybe next Tuesday, I can give you three questions about the parametric one. And also your TA can also give you some examples. Okay. And if needed, then maybe I can help you with some additional video for the parametric. Okay, so that's the surface area. So that's the calculus in parametric. Okay. Okay, let's move to just some introductions first for Polar. Okay. So usually, a polar coordinates, we start with the we call this the polar axis. We will have two components, the radius and theta. So we are going to determine the positions here based on the radius and the theta. So the positions, it can rotate, okay? And it's always start from here and rotate counterclockwise. Okay? That's we can consider as a positive movement. When it's moved from here, it's a negative. Okay, that's the rules in a polar system. So we call that this is P, this is R theta. Okay, and the interesting part on polar is in visuals, because it's always radius. So when you move around this space here, the radius is still the radius, right? But what about if we have the negative radius? How about that? Can we have the negative radius? It's a little bit tricky. But this shortcut how to find the negative radius is the behind on that radius. Okay. So let me show you. Let me show you. Let me maybe take this and copy here. Okay. Let me make the graphs first. Let me erase this part. Let's say we are having this theta plus pi. And this is the O. Okay. This point here is actually symbolized the negative of R. So r less 0, it lies on the quadrants of the opposite sides of the pole. So if you have this is actually same thing as like r, and then you're just adding the theta and plus pi. Remember that sine and cosine, they have the different value in different quadrants. This is actually similar things. Okay. So whenever you find any negative terms when you calculate the polar, it means that it's on the back side or on the opposite sides of those quadrants. Okay. Because you'll find it's confusing at the beginning, but if you follow the rules like this, then in all curves on polar, it's still the same. Okay, let me just give you example. Up here, let me just give you example. If we have the negative 2 pi over 3, the radius is positive, but the angle is negative, so it's going to have clockwise, right? Clockwise. So let's say this is the polar axis, and maybe this around here, maybe around that point. Maybe I will make it more straight like that. So maybe this is negative 2 pi over 3. Okay. And if you have, let's say negative 3 and then 3 pi over 4. So this will be, let's say this is the polar axis. Or maybe I need to make it more smaller here. Let me make it like here. So it should be going through here. Three over 4. So maybe it's going to have around here. Let me make it longer. Let's say this is 3 over 4 pi. The radius, if positive, it should be here, right? But because it's negative, it's okay. Or we can write this as in terms of theta plus pi. It's a little bit confusing for the negative part, but the whole polar, they will have the same rules for this one. Okay, that's the introduction of polar. And sometimes if the angle may be more than 2 pi, then maybe you will have that circling around. Okay. Okay. I think that's one thing that is important in polar, to define the negative r. Okay. I hope you have checked on the notes. Okay, the next one is just a review on what you have learned actually. Let's say this is y, this is x, this is r, and this is theta. And this point here we can say as in polar, or we can also say in Cartesians. So we have a conversion between polar and Cartesians, and I think you guys probably should have known this. Let me just write this. Okay. I don't think there is important here, but I think this is pretty much standard conversion from polar to Cartesian, or from Cartesians to polar. Okay, the next one is the polar curves, which means that we are going to take the r as a function of the theta. Or generally r theta 0. So whenever you have r equal to, for example, because we already know that the polar is a function of theta, then if we take this in terms of the polar axis, we will have several, let me just write down the polar first. Okay. Now we can take this and we can say that if this has radius 1, this has radius 2, and this is radius 4, then if we are going to have a polar curve that is just r equal 2, then it will be, or it symbolizes the circle with radius 2, okay, in terms of the polar curve. Okay. So let me take this in terms of r equal 1, r equal 2, r equal, let's say 3. So the curve, okay, the curve at this circle here, the curve consists of all points with r equal 2. So in terms of polar, r equal 2 will be a circle. Okay. Okay, so that's the first one, the circle. Second one, if you have a constant that is on an angle, let's say angle equal 2. Okay, let's just make it the same with the radius. Angle is 2. Which means that you have the polar axis, and let's say maybe here. This is just illustrations. Okay? Let's say this is 2, and we are making this all through to all point here. So at theta equal 2, it will be a straight line. It's a fixed straight line. So it fits with straight line. Okay, so that's two simple polar. Maybe I will put this maybe around here, and this one around here. Okay. Okay. The next. Okay. Let's say we have r2 cosine theta. And eventually, at the end, later you will see some patterns, and I think you can guess and maybe sketch easily from the pattern. Okay? But let's see how we can deal with the drawing the curves. Okay? So let's say we have 2 cosine theta. Okay. To make it maybe easy to draw, maybe you can have some special angle. Okay? So to help to navigate. Okay. We have theta maybe from 0, from pi over 6. Let's just use all this special angle. Let's say until pi over 2, like that. So this will be 2, right? Oh, wait, here. R cos theta. Pi over 6, this will be half square root of 3, this will be square root of 3, this square root of 2, this is half, so 1, this is 0. Okay, now how to deal with this? Okay. First, we can take the, remember this is not Cartesians. This we will draw the polar. So we are start from the polar axis. So this is the polar axis. when the angle is 0, it's all the curves is having distance 2, right? So angle 0 here. So we will draw from 0 maybe until pi over 2, and maybe until pi maybe. But let's say we have first 0. So let's say we set 2 maybe around here. Let's set that way. So we are setting maybe around here. This is 2, 0, which means this is the r theta. Okay. Why this is okay? This should be 2. Sorry. Okay. And then we move on to, let's say we draw the pi over 6 maybe around there. Maybe around here, this will be square root of 3 and pi over 6. Okay. And increase maybe around here. This is the square root of 2 pi over 4. Okay. So we increase, and then this will be maybe around here. This will be the 1 and pi over 3. And then lastly, we have 0 here. Now, if we try to find until pi, we can try as well. We can check this, and this will be a negative, right? A negative. This is precisely the same value, but with the opposite signs. Okay. Okay. Now what will happen after 0? After pi over 2, we will have 2 pi over 3, which should be around here, right? But since it's negative, we move to here. Got it? Okay, got it? Okay. So since we are going to have this particular range here, we will have at this point, which is the -1 to pi over 3. And then exactly mirror, if you check the other one, it will exactly mirror the signs here. And when you complete the curves, it will be a circle. Okay? It will be a circle. Yeah, let's say it should be a full circle like this, but I think I don't make it like into more proportional, but it should be a circle like this one. So maybe we can change this a little bit here. Should be a circle. Okay. Cosine theta is a circle. Later on, with the same techniques, if you put negative at this equations, so This is positive 2 cosine theta. If you multiply with negative, it will be on the left side. Okay. If you change cosine with sine, if you have a positive one, you will get the top here. If you multiply with negative, it will be down here. And you will see a pattern. Then you will see a pattern. And it will help you to understand more and help you to at least calculate. Okay, to calculate. But before we going to another sections, how to convert from the r equal to cosine theta? Let's convert to Cartesians. We can have this x is r cosine theta, and cosine theta is x over r. So we will have r 2x over r, which we are going to have or we can write down like this one, okay, and we can simplify this into a circle equations that we have, and we know the center, right? Can check this. Okay. So it's true that this 2 cosine theta is a circle, and we can confirm that through the Cartesians. Okay. If you would like to, you can also try the maybe 2 sine theta, or maybe the negative part of this one, negative 2 sine theta. This whole thing will become negative, and this will be positive. This will be here to left side, right? At least there are several types of polar curves. Circle, and then later you will see some interesting shape, like a flower shape, and we call the limaçon shape, cardioid shape, like a heart in a human heart. Okay, and it's interesting, but eventually you will know that there is a pattern to know which one is the one. Okay, so 2 cosine theta. Okay. Okay, let's move to another shape. This is circle. Let's move to another shape. Okay, let's move to this next line. Okay, let's start with this 1 plus sine theta. For now, it seems that no particular pattern, but I will give you later the pattern. Okay. So 1 plus sine. We can draw in terms of Cartesians. to see the value, okay, we can also use the table, but let's just throw the graphs. So let's say this is theta, this is theta, this is the radius. And let's say this is 2, this is 1, this is 0. And let's say we have pi over 2 pi, 3 over 2 pi, and 2 pi. Sin theta at 0, it's 0 plus 1, so we'll start from this one. And then it will increase up until equal to, maybe around here. And then 0 will be here. Maybe it will be around that. Okay, maybe like that. Okay. Now, if we use the polar, so this is in Cartesian. So what would this graph looks like in polar? So we start with the polar axis. And let's say we have the line for theta is pi over 2. When theta is 0, r is 1. Let's say this is 1 and this is 2, this is 1, this is 2. Let's say this is 1 here. So maybe we start from here. And then it should be increasing, right? It should be increasing. When you increase the angle from here, from 0 to maybe some other value here, you can use the special value if you would like to know, maybe using pi over 6, pi over 4, pi over 3, and you will see that this will be perfectly like this. Yeah, maybe like that. Maybe not too smooth. Okay, maybe like that. And at pi over 2, it's 2, right? The radius. And then after that, you can continue to move on to the other quadrants, and we will see that this will perfectly also mirror the right side image. So this is when theta is equal pi. And then, when it reach out the 3 over 2, as we see from the Cartesian, it's reached 0. So we will go like this. Okay. And then it's going up until 1, which is perfectly matched with this one. Okay. This is what we call the cardioid. The cardioid shape. It's one of the lemmas. And how to tell the cardioid or not? It's basically depends on the ratio, but a little later, maybe that will be the later part. This is 1 plus sine. Okay, 1 plus sine like this. I will give you a little bit shortcut on how to look on positive and negative value. Okay? So, on the previous polar, we learned about at least the r cosine theta. Right? R can be any constant, 2, 3, 4. We know that the cosine will have the curve like this. Right? Okay? And like I said before, we can also have the negative one here. Okay? So we can have the other one. So this is negative r cos theta. This is r cos theta. Okay. Now, if we have the r sin theta, if you check, the positive one will look like this. Okay. The negative one will look like this. Okay, now look on our cardioid. This is 1 plus, right? 1 plus sign. The sign itself here is positive. Look here. It's a little bit at the top. So what's happened when you have 1 minus? Should be here. What happened when you have 1 plus cosine? Should be here. The same thing happened when you have the negative cos here. And I think it has a pattern. It has a pattern. But the basic pattern is using this from the circle. From the circle, you can see the pattern. Later on, it will be a little bit useful to recognize the curve of this. Remember, we are not doing any calculus yet. We just introduction in the polar. And how to tell this cardioid, this is based on the ratio. Or we can write the terms in r, let's say sine and 1 plus minus r cos theta. Depends on each radius, okay? And positive negative will determine which sides that the curves will be. The r will determine how the limacon is, sometimes it can have some loop, like go inside here. Or sometimes it can have like, it's becoming more and more like a circle, but not as a circle enough. Okay? So it can have like some slight change in this part here. But later I will just let you know the ratio. There is certain ratio that we will have a difference in the shape. Okay. And I think for today's I will stop just up until here. Okay. We still have at least 2 other shapes that we need to look on. The first one is the rose, like a flower, and the last one is we call the lemniscate. Lemniscate. It's like an infinite, like that, like 8. But that will be the Tuesday next Tuesday class. So we will stop until here. Okay. Any questions? Any questions so far? And I think I can attach some video for you. I think I just grabbed from some YouTube channel that explain this polar shape, and I think it's helpful. It's short video, and I think you can get some point of view from the video. Because this is not the calculus. We are not yet calculus. Okay, this is just an intro. Okay, so that will be today's class. So see you next week. Okay. If you still need the code, let me know. Okay.